Hello, and welcome to sections 6.1 through 6.3. In this video, we will be introducing the method of joints and some concepts you'll need to solve problems using the method of joints. So the method of joints is used to analyze trusses. Trusses are structures composed of slender members. And so I have an example of a truss over here on the document camera. So you can see we have four slender members represented by these connects, and I can connect them with one another to form a square truss. So trusses have some assumptions behind them. So those assumptions are as follows. All forces, internal and external, are applied at the joints only. So for instance, if I wanted to apply a force to this, it would only be at the joints. This means the mass of these members are neglected. Also, you probably noticed when I pushed on this it rotated. That's because members are joined by smooth pins. We do this so that each of these members is now a two-force member. If you remember, two-force members have a special property in that we know the force in that member is only along the line it's axial, so it just follows the member's direction. So it simplifies our analysis. Now, these square trusses aren't very useful for what we're going to do. They add in this rotation aspect, which we don't want to analyze. So instead, we use simple trusses when we do our analysis. So simple truss is just another word for triangular truss. So it's just something that's been triangulated. So if you push on it, again, apply forces only at the joints, it doesn't deform. It just stays in its shape, but the whole body can rotate. So it basically makes it into a rigid body. All right. So the method of joints is going to take these simple trusses and, there we go, deconstruct them into multiple particle equilibrium problems. So we imagine cutting through the members to expose the internal forces. So that would look something like this. So say we cut this member, then we might have, I know the color changes, but pretend with me. So we cut our truss and we expose the internal forces so that we can see what is going on. We can do the analysis with those. So we now have roughly the same truss. It's still a triangle. And let's get that kind of lined up. There you go. But now we have three different free body diagrams. The one over here, the one up here, and the one down here. So let's focus on just this one. So this is the one that I was holding still. So I'm going to remove these. And so say we focused in on just this one. Well, I was treating it as it was pinned, so we would still have our external forces. So we might say, oh, we have an AX and we have an AY because it can't move. But now we also have forces in these members. Because I have cut through them, or imagine cutting through them, I have exposed these forces. So now we can do an analysis, which is just a particle equilibrium analysis, and find those forces. So for instance, I might draw this force outward. So if I draw the force outward, that is going to be a tensile force. So you could imagine there is another piece of the member up here. So in order to cancel out this one, and I'm going to put it over here, would have to have a force going down this way and up this way. So this piece, if I moved it over here, would do the same thing. I would have my force coming down. But if I look at this force, and you could imagine this is a piece of Play-Doh, if I pull on this, it's going to stretch out. This is said to be in tension. So forces that we draw outward from our free body diagram are in tension. Let's look at the opposite case. Let's say we had this force going inward. So if this force is going inward, and I take my other member, so then to balance this cut out, because again, when I put the cut back together, I need my forces to balance. so that I'm back in equilibrium. Otherwise, we don't have a rigid body. So if I take that, and I will put my member right here. So it had a force pointing in, and a force pointing in, because then the member also has to balance. This force, you can imagine pushing in on both sides of like a piece of Play-Doh, it would squish. This is said to be in compression. So when I draw arrows into my joint, that is a compressive force. And we need to know if we are assuming a force to be in tension or a force to be in compression. And when we go through the math, we're going to get positive numbers or negative numbers, and if we get a negative number, it just means we guessed the wrong sense, either tension or compression. All right, so in the next video, we're going to use these concepts to find the internal forces in an example truss.